I've done one of these video lessons, so I figured I'd do that. You're probably sick of Khan Academy by now. So it's not perfect, but it helped us get through quite a bit of material and at least get you introduced to some material that I was really having a difficult way figuring out how to teach you. I would have rather had you be working with wires and circuits and switches in the class, but that's how it goes. So you haven't seen me for a while in video. My hair is quite a bit longer. I need a haircut, but we got 9 days left, so we've got a number of pretty interesting things to talk about here. We'll start by talking about a little bit more about light, but light in a different sense. Light is a wave, and then what light and waves, including other waves, can do. So the point would be that you would be taking notes in some form or fashion while we're doing this, either digitally or in your notebook, as you were used to doing back when we were still meeting in person. So in some sense, this is not a new topic, and it's not a topic you haven't heard about before. We've talked about in class before we all got sent home constructive and destructive interference. We've talked about if waves are in phase. For example, if you remember me playing those loud and annoying tunes in the classroom and having you guys shift left to right or front to back, where the sound waves were in phase, we had constructive interference sounds. Where sound waves were out of phase, your sounds, the waves cancel each other out in destructive interference. And so now of hearing those areas of constructive or destructive interference, we're going to see them with light. So that's kind of the basic summary of this. And by the way, I'm going to go a little fast here, so you can always pause the YouTube video as you're watching if you need to get caught up with any of this. So as it turns out, when we have light coming from multiple sources, just like when we have sound coming from multiple speakers, we can get constructive interference if the crests and the troughs line up with each other. That's constructive interference. If, however, we have light coming from multiple sources, just like when sound comes from multiple sources, and the crests line up with the troughs of other waves, these two waves destroy each other and create destructive interference. Even though photons or light are hitting the spot on the screen, you actually will see a dark area. There will be nothing visible because this light essentially cancels out this other light. This is what this looks like if I was able to have a laser pointer and a diffraction grating just like this set up in the classroom. We would turn off all the lights and I would actually be able to show you this. The central peak here, the first bright fringe and the second bright fringe, and so on and so forth. Well, as it turns out, there's a way to calculate how many bright fringes you see and how far apart they are. That is to say, what angle those fringes are visible at. And so here's the equation: d sine theta equals m lambda. Don't worry about the plus or minus there. That just means to the left or to the right of that bright fringe. So it's symmetrical. You see them on both sides. M equals 0 represents that bright fringe in the middle. And then m equals 1 represents that first fringe plus or minus 1 on the other side. M equals 2 represents that second fringe plus or minus 2 on the other side as well. Here is how the destructive interference pattern is found. We just offset it by a half, right? So if we're halfway between 0 and 1, we would have that m be equal to 1/2. This would be 3/2, and so on and so forth. So this is how you find bright fringes or constructive interference. This is how you find the dark fringes between the bright fringes. Also notice that we have d, the spacing between these grooves, and we have lambda, the wavelength of the light. So you should remember that all these units need to be, all these measurements need to be in the same unit. If you put everything in meters, that's great. If you keep it in nanometers, that's great as well. Theta doesn't have any units and m doesn't have any units. Here's a practice problem. See if you can get the answer. Diffraction gratings break light into their respective wavelengths, and that's because, as you can see here, the wavelength affects the angle that the light is bent at or diffracted at. And so actually, if we were in the classroom, I would have you take a look at light coming from a light bulb through one of these diffraction gratings, and you would see a rainbow pattern. Here's a quick look at the resolving equation. I'm not sure if I'm going to have you do a problem with this, but basically, given the space between two grooves and the wavelength of light, you can calculate a minimum resolution, a minimum angular resolution. That is to say, you can tell that two things are some minimum angle apart with a given space between the grooves and a given wavelength. Again, just to recap, the problems will be using these two equations. D represents the space between the holes or the grooves. Right here, the space between these grooves. Theta represents the angle that the light is bent or diffracted at. M represents which bright or dark fringe you're at. And lambda represents the wavelength of the light. Just again, a reminder that D and lambda have to be in meters, or they can both be in nanometers as long as they're in the same unit. M and theta don't have units. Well, good luck working on the problems as we get through these over the next day or two. And as always, contact me if you have any questions. Take care.